All right, so far in the unit of vector calc, we've covered the notion of a vector field, covered the notion of a potential, and we've covered the idea of a force field, which is a vector field that models forces. Anyways, what we now want to do is we want to consider the idea of a line integral. Now, the line integral is going to not seem particularly useful to vector calculus just yet, but once we apply it to vector fields, it will be applicable, obviously. But we're going to start off a little bit more simply first, just with the idea of a function as opposed to a vector field. It will make things a little bit easier to start with. But anyways, let's consider the definition. So the definition really is derived from something that we covered in Calculus 2, which is that if I want to find the arc length of some function between a and b on the x-axis, I can integrate between a and b, and I take the square root of 1 plus the function squared, derivative of the function squared with respect to position, right? So that's how I would find the arc length of a function if I just have a curve up here and I want to find this distance between a and b, right? And then we also covered in single variable calculus the idea of a parametric equation. If I have something that looks like this, like that, and this is t equals a, this is t equals b, then I could generalize this definition, find the arc length of this, and this is the integral between a and b of the square root of x derivative with respect to t squared plus y derivative with respect to t squared. And I take that with respect to t, right? Now that's easy enough. That's finding the arc length of a parametric curve. Now we should be all familiar with parametric curves. We're going to take this one step further. If I want to take the integral of a function along an arbitrary curve, then I say that I'm taking the integral over c of f of x and y ds. And then this is equal to the limit as n approaches infinity of the sum from I equals 1 to n of f of x, y, delta s. Now, what this really means is I have a graph here, and this it would be useful to maybe model the function as a color plot or something like that, or a topographic map of level curves. Let's say we have a color plot of our function, and I'm going to take a curve c, and I'm going to move along this function. So the function is assigned, there's a value of the function here, there's a value here, there's a value here, there's a value here, there's a value here. There's a value at every single point on this xy plane of that function. And this curve c moves along the function. And what we're essentially doing is we're finding, you can consider this as a rod. Consider this curve like a rod, and the function determines what the density of the rod is as we move along. And what the line integral is doing is it would be telling us the full weight of the rod because the density changes. So it tells us the full weight of the rod when we integrate along this curve. Okay, so now we need to determine what the heck delta s is. Well, that's fairly simple. It's our similar definition from the parametric definition. ds equals the square root of x squared dot plus y squared dot dt. Okay? Now this means that you need to put this curve in terms of t. You can't put it in terms of x and y. And if I want to find the integral of f of x and y ds, then I'll just integrate from my starting t to my ending t. Then f should be written in terms of x and y of t. And then I multiply it by ds, the square root of x dot squared plus y dot squared dt. So that's all well and good. What if my curve is piecewise differentiable? What happens if my curve is piecewise? What if it looks like this? Maybe there's a little circle there, then it goes back down here, then maybe it goes over there. Well, I can divide this into a discrete amount of line integrals. So if I want to find the line integral over a curve, I can split that curve into however many sections I want, and that allows us to integrate properly. The other thing is, if I maybe do this, if I close this, then we have a fancy way of defining that. We say that's the integral over the contour, but we put a little circle there to indicate that it's closed, of f of x, y, ds. And we'll talk more about the contour closed loop integrals later. But that's what it means. If there's a circle on top of the integral, that means that it's closed. The line that you're integrating over C would be closed. So you can draw your pencil all the way around and end at the same place you started. Let's try an example. Let's evaluate the line integral of 2 plus x squared y ds on the upper unit circle. So the upper unit circle looks like this. Again, my apologies for my drawing here, but that's the unit circle. It looks a bit elliptical, but that's okay. We go from 1 here to -1 there, and then we've got 1 here. So that's the upper half of the unit circle, right? So if you remember, the parameterization for the unit circle is one that we should know, is the transition between polar and rectangular coordinates. So let x equal to cosine of t, then y will be equal to the sine of t. That should make sense, right? That models the translation across this curve, so that's our curve C, and it goes this way. And if I want to find ds, then I take the square root of, well, the derivative of cosine of t is negative sine of t, but then I square that, so that's negative sine squared of t. And then that's plus the derivative of sine, and square that as cosine squared, right? And then I can get rid of that negative sign because we squared it. We get sine squared plus cosine squared, that's 1. So I get ds is equal to 1 dt. So now what we do is we perform this integral, and note that our starting point is theta over here is going to go from, or t is our variable, t models the rotation, t goes from 0 over here to pi over here before we stop. So we're going to have the integral from 0 to pi of 2 plus cosine squared of t times sine of t, because x squared is cosine squared, because x is cosine, and then y is sine, because obviously y is sine. And then ds is equal to 1, so ds is dt. Now we can perform this integral fairly easily. We take 2t out of there, obviously, that's easy. And then from here, you could do a mental u substitution, whatever you need. You take the integral from 0 to 2 pi. Note that the sine is the negative derivative of the cosine, so you get cosine squared of t times the negative d cosine t. And then you get you get 2t minus 1/3 cosine cubed of t, because you just integrate with respect to cosine of t here. You have cosine squared. Move the 1/3 out and raise the power. Then you evaluate between 0 and pi. Then that evaluation is fairly trivial. You get 2 pi plus 2/3. Okay, I hope this all made sense to you. The intuition made sense. It's really just what we did in parametrics, and then tacking the function on to the end of it, assigning kind of a weighting function or a density function, if you will. Anyways, in the next video, I'd like to kind of bump this up another dimension, talk about motion. So what if our curve is in 3D space? You can think about maybe like a helix. A helix is a cool shape. It's a helix around the z-axis as your curve. That can be kind of fun. Or a line, or whatever you need. Later in the unit, we'll be looking at planes. And then eventually, when we get to this level, we'll just be using vector fields as our function that we have. Right? All right. That's all I've got. We'll see you in the next video where we'll talk about some 3-dimensional line integrals.